I think we can start. So in this part of the lecture today, we will have two other paper presentations. And seems like we keep doing illegal operations with DRAM devices today. In the first two talks, we did some reduced latency operations. And in this one as well, we are looking at the conditions in the reduced voltage operation and how it affects latencies and stuff. And let the last talk be a surprise for you. So my name is Giray, and today I'm going to present this paper called Understanding Reduced Voltage Operation in Modern DRAM Devices. This is a work we did in Carnegie Mellon University as Safari Group, and yeah, at that time we collaborated with NVIDIA and ETH. So we internally call this paper with name Voltron because it's the name of the mechanism in this paper. So you can get used to hearing Voltron. Okay, so here's an executive summary. So here we tackle the problem of DRAMs having large demands of power, and they consume a lot of energy in many systems, and we want to reduce it. So this is our problem here, and we see that existing technologies are already trying to do it with reducing the voltage. And our goal here is to understand and exploit the reliability and latency behavior of real DRAM chips when we aggressively reduce the voltage operation. So we are pushing the limits here. And we have three key experimental observations in this paper. One of them is when we reduce the voltage, it introduces errors. And the second one is we see that these errors are clustered in particular locations in the DRAM chip. So they have some special locality. And when we use higher operation latency with the reduced voltage, then we can get rid of these errors. So there's a trade-off there. And based on these, we propose the mechanism Voltron. It's a new DRAM energy reduction mechanism that reduces the voltage of the DRAM and increases the latency accordingly to sustain the reliability. And it uses a regression model to meet some maximum performance loss target. And at the end, we see on average, we can reduce the energy by 7.3% for many systems. So here's some motivation. So we see that by referring to the older papers, we see that this DRAM is widely used, and it consumes more than 40% of the total system power. So reducing it is going to have some impact on the overall energy consumption. And we see that reducing the voltage of this memory is a way of reducing this energy consumption. So this is a formula or like a relation that you remember from other classes probably. The system power consumption is proportional to the square of the voltage, so it's effective to reduce the voltage. And in the current technologies, we see that this DDR3L is a variation of DDR3 standard of the memory, and it just adjusts the DRAM chip in a way that it's going to work with lower voltage level. And by doing that, it's able to reduce the energy consumption of the DRAM chip. And when you look at LPDDR4, which is widely used in mobile devices, you see that the supply voltage of that is also much smaller than the nominal voltage of DDR3 or DDR4. And the question is can we reduce DRAM even further, DRAM voltage? So, okay, we have two goals here. The first one is the understanding and characterizing this various characters, the DRAM under reduced voltage, to understand how it behaves and what are the trade-offs there. And second, to develop a mechanism to exploit those observations. Here are our key questions. So the first one is, how does reducing voltage affect the reliability? And the second one is, how does reducing voltage affect DRAM latency, assuming that we can sustain the reliability? And how do we design a new DRAM energy reduction mechanism? So I'm going to give a very brief background on DRAM. Since you already know, like you saw this a lot of time, I'm just going to keep it short. So here you have a CPU and it's connected to a DRAM module or an off-chip link called DRAM channel, right? And in each DRAM module you have a chip. You have many chips. And within each of these chips you have two sorts of circuitry basically. One of them is called peripheral circuitry that includes the control logic and the I/O. And the other part is DRAM array that you keep seeing this two-dimensional arrays of DRAM cells. And these DRAM cells are connected in the rows as word line, that you activate a word line to access to a row of DRAM cells. And then to read or write each individual DRAM cells, you need these bit lines to access them in columns. And how you access them is, again, a similar animation to the previous talk. So you first need to activate to reach to the cells here. So you activate the word line, and the voltage level is sensed by the sense amplifiers in the bottom. And then you read from the sense amplifier. And then you pre-charge it back to get prepared for the next activation. And when we look at the latencies, this row activation and pre-charging the bit lines takes a long time basically in accessing these DRAM cells. So let's move on to the characterization. So how we do this characterization is a little bit important actually in this talk. So we have this supply voltage rails going to these chips in a DRAM module, right? So we adjust the voltage on these rails. And to be able to do that, we use a FPGA-based infrastructure called SoftMC, probably you heard about it. And we use a voltage controller device from Texas Instruments to adjust this voltage levels on these rails. So obviously we use real DRAM modules here. And then we schedule DRAM commands precisely by using SoftMC so that we can have fine-grained control on the latencies between commands. And in this work we test 124 DDR3L chips, and yeah, these are some details about them. You can look at them later, or you can find more details in the paper as well. So the important thing is we iteratively read every bit in every one of these chips, and then change the supply voltage level from 1.35 volt, which is the nominal voltage, down to 1.0 volt. Which means like 26% of voltage reduction, and we see how these chips behave. Okay, so here are some results. So on the x-axis you see this supply voltage, and we start from the rightmost end, which is the nominal voltage. And I will see you some curves with different colors. They belong to different major DRAM vendors. And on the y-axis, you see how errors pop up and what kind of bit error rate you see on those chips. So when we reduce the voltage, we see that each vendor behaves differently, but there's a common trend that until reaching some minimum voltage, you don't see any errors. So we have a guard band clearly. So we don't have to make these chips work at 1.35 volt. If you use vendor A or B, you can go down to 1.15 volt without any reliability issue. And after that point, we see that suddenly a lot of errors keeps happening. Okay, so this is the main takeaway. Okay, so let's look at the source of these errors. So to understand it, yes?
Is this something measured at the worst case scenario, like measuring with respect to voltage, but other conditions like temperature and all, it will keep up the worst case scenario?
Yeah, so yeah, the question is about the worst case scenario. So here, this plot, I believe, comes from a room temperature measurement, but we change the temperature, for example, to 70, 80 Celsius, and then we see similar trends. So actually it doesn't change that much when you look at the actual values, but you see slight changes like this. Error rates increase at this voltage levels a little bit more, but the general trend is like this. And again, you have this V mean voltage that you have reliable operation even in high temperatures. So to understand the dynamics of this, we step back from experimental study and then we do some SPICE simulations to understand the circuit a little bit. So here we have a circuit model that we reduce the supply voltage, and then we observe that the activation and precharge operations happen in a larger time window when you reduce the voltage. And we believe that this is the source of the errors that we are observing in the previous plot. So then we go back to experimental study and test it. So here I will show you. So yeah, measured minimum latency that does not cause errors in DRAM modules happens like this. So here we see a bubble plot. Here the bubble sizes show the population of the DRAM chips that we observe at that. We observe reliable operation at the given point of voltage and latency on the x and y axis respectively. So this comes from one of the vendors for brevity and simplicity. So from 1.35 volt to 1.15 volt, this should be vendor A or B, right? Actually 1.125 volt, you have 100% of the chips working, right? Because this value is 1.0, like all the population is there. And then after some point, you see that we need to increase this activation latency for reliable operation. So if you look at the x-axis and find 1.1 volt, you see that 90% of the chips work with this latency around 10 nanoseconds. And then for the 10% of the chips, you need to increase this activation latency to 12.5. And then you have the reliable operation again. So this proves that this is actually a source of this reliability issue in the reduced voltage operation. And after some point, you see that when you add up the columns, it doesn't reach to 100%. Then it means that whatever activation latency value you put there, your DRAM doesn't work reliably. So you cannot operate in that voltage. You can't rely on that. Okay, I already talked about this. And the key takeaway is DRAM requires longer latency to access data without errors in the lower voltage. And here is another observation that we had. This is a nice heat map that shows the bit error rates locations in the by the rows, basically, in a DRAM chip. So on the x-axis you see the banks, and on the y-axis you see the rows, and the color over there shows the bit error rate of each individual rows. So this is a very nice clustering of the bit errors, right? So clearly we see that some banks are more vulnerable to this kind of errors than others. And not all results look like this. When you go from vendor to vendor, for example, you see clusterings not in the banks but in the rows, for example, or parts of the banks. But we see a nice special locality in many of these chips. And we have some other results in the paper about this characterization. It's quite a long paper, actually. It's like 40 pages. You're welcome to read it. I'm not sure if it's in our required readings. Is it required? Probably it's required. Okay. Yeah. Good luck. So, okay. Here we also do some analysis by using some ECC, a simple ECC mechanism to see if it can help reducing voltage furthermore. But we observe that it's not very sufficient, because when we start seeing errors, it just pops up very in very large numbers. And we check the effect of temperature. Yes, high temperature requires higher latency under some voltage levels, but general trend is the same. The story is similar. And when we look at the data retention time, we see that reducing the voltage does not affect the retention time that much, actually. So here the key, I mean, it's a bit surprising, actually, because when you reduce the voltage in the capacitor as well, right? So you would expect it to leak faster or have like lower retention time, so you need to refresh it more frequently. But it turns out that it's not the case. Probably there's some reduction over there, but within the given refresh rate, we are able to satisfy a reliable operation. And we also repeated these tests for many different data patterns, and we do not see a statistically significant difference across those data patterns. If you have a 1 or 0 in a cell, it doesn't really matter that much. And yeah, if we summarize the key experimental observations, so okay, we reduce the voltage and the error rate increases, and then these exhibit some special locality, and increasing the latency can give us some reliable operation. And okay, maybe we can give a quick pause here and then discuss, like, if you guys have any ideas of how to make use of these observations. So what kind of mechanism or method you would apply to get benefit of these, basically? Any ideas? No? Okay. Okay, luckily in the paper we have a mechanism called Voltron. This is a DRAM energy reduction mechanism, and the goal of Voltron is to exploit the trade-off between this voltage and latency. And the approach is to reduce the DRAM voltage reliably, means increase the latency. When you increase the latency, you would expect some performance loss, right? Because you're accessing to the data in a larger time period. So the goal of Voltron is to satisfy this with modest performance loss. Actually, here we see a trend. This is like a motivational data here. So when we reduce the voltage from 1.335 volt to this value, for example, assuming that we can make those chips work with increased latency. So when we come here, we can see some DRAM power savings increasing. Also, performance is reducing. So there's a trade-off here. So you don't want to lose performance, because when you lose performance, then your application finishes in a larger time. So energy is power multiplied by time, right? So you can end up losing energy, actually. So you want to keep performance loss in a target window. Okay, so here's a cartoon showing the Voltron's overview. So how Voltron works is the user comes and specifies a performance target loss. He or she says that, okay, I'm okay with 5% performance loss target. And then Voltron does some magic, and then comes up with some operating voltage and latency parameters. And then at the end, you use those parameters while running your application, and then you save some energy. But how do we predict this parameters here? What kind of magic we do over there? So this highly depends on your application's characteristics and your DRAM's characteristics. So to be able to come up with this parameters, we use a linear regression model over here. And we look at the applications characteristics and DRAM's characteristics. We try this application characteristics with different voltage levels, and then we predict some performance loss for each of these voltage levels. And then we compare our target with the performance loss we have, and then we decide the final voltage value for this. So the application characteristics we looked are two things, very simple. One of them is memory intensity, which is the frequency of last level cache misses. And the other one is memory stall time, which is the amount of time that your processor actually stalls waiting for a memory request to be served. So you can get both of these characteristics from some profiling tool, like for example Intel has a tool called vTune, or you have this Linux tool that you can use on many machines called gperf. They give you this kind of matrix when you run an application. And what happens if we are running more than one applications at the same time? Then we act conservatively here. We set the parameters for the worst case. Okay, let's compare it to the prior work. In the prior work, it's already proposed in 2011 that we can dynamically scale the frequency and voltage of DRAM chips. So the problem here is when you scale the frequency and voltage, then you set everything to the low voltage, and then your I/O frequency gets reduced. Then you lose some bandwidth as well, and this causes you high performance loss actually. But in Voltron, we are proposing to reduce the array voltage only instead of the I/O peripheral circuitry. So peripheral circuitry can keep working on high frequency, but within the DRAM array we use large latencies. And the key idea here is, to exploit the special locality is that, let's say we see some accumulation of the errors in certain banks, then we can apply different banks, different voltage levels, or we can also apply different voltage levels for different chips as well. So we can get benefit of this. So obviously you cannot do this in the commodity DRAMs today, but with a very little support from DRAM chip, then you can do that. And we evaluate this mechanism by using MACPAT and DRAM power for the energy calculation, energy measurements. MACPAT is measuring the energy of the CPU here, and then DRAM power is for the DRAM, basically. And then we use a realistic system, and we run some spec benchmarks and YCS benchmarks, which are like representative of the common applications. And we compare our work against this MEMD-VFS, which is you scale the frequency and voltage together. So here are some results. So on the x-axis we give some average values for all these applications, and we cluster them as low memory intensive and high memory intensive. For the low memory intensity, you see that you can see that 3.2% improvement, and for the high memory intensity, you can see 7.3% improvement. Obviously, we have higher benefits with the higher memory intensity workloads in the energy savings. And when we look at the performance loss, for this evaluation, we set the performance loss target to 5%, and we can satisfy this energy saving within the targeted performance loss. So your application still runs in a similar performance, and you save energy. It's pretty good. And the important thing is, for both low and high intensity workloads, we can see this energy savings and performance target match. And yes. Okay, to conclude, we have this DRAM devices that consume a lot of power, and then we need to reduce. We want to reduce this energy consumption, power consumption of these DRAM devices, and we want to aggressively reduce the voltage for that. And we do some experiments with the real DRAM devices that shows us that errors occur with lower voltage, and they have some special locality, but we can get rid of them by increasing the latency. And we propose Voltron, a mechanism that uses a regression model and uses the characteristics of these applications and the DRAM devices, and gives you a system energy reduction. And yeah, this is the end of the paper. Do you have questions? No? Okay. Okay. And here's some food for thought. Now you know about Voltron. Yes, sure.
The linear regression the best model possible for this prediction or not? Because why would it depend linearly from every parameters?
What every parameters?
Would you use the behavior of the aggregation and the run latency parameter, but why would this parameter, why would the relation be linear between, perhaps the performances influence the model in quadratic ways, anything like that?
Yeah, if I understand correctly, so you're saying that we are just using these two parameters from the application, and we are just using a simple linear regression model, and can.
Did you try other models?
So yeah, that's a very good question, and that's one of the things that I want to ask here actually. So this is a mechanism, right? And the major contribution of this work is to show this trade-off in the real DRAM devices. And here's a way of exploiting it. But obviously, there can be better mechanisms. Linear regression is a very simple machine learning technique, right? And the metrics we are looking at, yes, they're intuitive, but maybe we can get benefits of looking at other metrics as well, like, I don't know, maybe reuse distance. I don't know. Because there are a lot of dynamics in your system that when you think about the memory access patterns. And maybe in some parts of the memory, we have this high intensive accesses. In some parts, we have low intensive accesses. Maybe for a while, it doesn't go to the memory at all. So maybe we can improve our mechanism based on these, right? So the quick answer to your question is probably it's not the best mechanism. But we should talk about we should think about how can we improve and how can we come up with a better mechanism. So I'm open for ideas. So another thing I want to ask you guys is that, so Voltron is asking users to define a target performance loss, right? So user should specify something. And it is about the performance. And when we reduce the voltage, we save power. And as I said earlier, energy depends on both power and performance. So what do you think about combining these three together in a more automated system that maybe user does not require to specify a performance target loss? Target performance loss, right? Yeah, these are things for further thinking. If you come up with ideas, you can send us to us and we can discuss. Maybe you can publish another paper on top of this. Yes.
I think this method will be more effective when we have a lot of switching, because if we see the power calculation, then the dynamic power consumption is the one that depends on the voltage square.
Yes.
And it depends directly on the frequency of the operation.
Yes.
And it has the activity factor attached to it.
Yeah.
So when we have a lot of activities in the circuit, then it will grow linearly with the activity, like the power consumption. But if the voltage is higher, then it will go like quadratically with the voltage.
Yeah.
So in those circuits, I feel like it should depend on the application. It should not be a fixed thing that user has to give. But I feel it should be something that depends on like what pattern we are feeding to the complete transistors. So that should decide like whether we should go for this trade-off or not, or how much.
So I'm lost in the last part, the register part.
So because like first thing, the activity is something. So the power consumption will grow with the activity linearly because it's directly proportional to the activity, but it is related to voltage. It will grow quadratically because it depends on the voltage square.
Yeah.
So in that case, so if we have a higher activity in any circuit, if we do a comparison between, if we don't implement this method and we implement this method, so there will be a huge difference. We'll see if the activity is much higher. Like the pattern we are feeding is like randomly 1010 rather than having a stable value.
Yeah.
In that case, it will be more significant. So it should not be only that the user has to give this specification as the performance, how much performance trade-off we can do, but at least we can also judge from the application point of view, like if we are feeding this information.
Yeah, I think it's a very good direction. Yeah, I think you can get further benefits by applying that kind of dynamic mechanism. If there's no other thought or question, I'll go and ask from another aspect. So here we see some trade-off of DRAM parameters, namely voltage and latency, and reliability. So this was our takeaway, right? Reduced voltage and increased latency sustains the reliability. So if we change the claim to reduced voltage and reduced latency hurts reliability, can we say that enabling energy efficient by reducing voltage and high performance by reducing latency for approximate computing makes sense? So what do you guys think about that kind of direction? Do you have any workloads in your mind that can get benefit of some approximation about this? Okay, so maybe we can give some example in the next talk. What do you say? Okay, yeah, this is the end of the presentation. If you have questions, you can email us, you can ask on Moodle. Yeah, ask on Moodle is better. Yeah, so that everybody can see that and we can keep brainstorming later on. Thanks.